Well, my dear students, now in previous lecture, I have turned it on for the Shannon's capacity theorem, and I have told you that the Shannon's capacity theorem it largely depends on the signal to noise ratio. Why? Because Shannon just take the practical thing that you can't avoid noise while you are sending a data. So while you are sending a data, you are not available to just enforce the noise or just you can remove or revoke the noise. So he states about a ratio that is known as signal to noise ratio. That is the signal power to noise power, the division between signal power and noise power. If the signal power is greater than the noise power, the signal to noise ratio become greater than 1. It's high quality. If it is equal, it's okay. If it is lesser than that, so the noise will overpower the signal power because the noise power is on the denominator side and signal part is on the numerator side. So we have to maximize signal power. We have to maximize the signal power to achieve the great to achieve the good amount of signal to noise ratio to get the capacity, the well capacity or data rate to be higher through the channel. The Shannon capacity theorems puts a limit on transmission data rate, not an error probability. So theoretically, possible to transmit information at rate RB, and it's less than or equal C with an arbitrary small error probability by using a sufficiently complicated coding scheme. And for an information rate RB is greater than capacity, it's not possible to find a code that can achieve an arbitrary small error probability. So there are two limits on Shannon capacity theorem. First limit is that if the capacity is greater than the bit rate, or you can say that information rate, so it will be an arbitrary small error probability by using a sufficiently complicated coding scheme. But if it is greater, information rate is greater than the capacity, so it is not possible to find a code. That means if the bit rate is higher, so you need to have a good capacity rate to just overpower it or just accumulate the bits out of it. That's the thing. Okay. Now you can see a practical reason and the unattainable reason. Okay, on Shannon capacity theorem that we have found a chart or graph from real life experience, as you can see. As you can see from real life experience, that's the reference part. Oh, just see the part that is the attainable reason, that's the attainable reason, and there's the practical reason. Okay, it's the practical reason. So we start the signal to noise ratio from minus 10 to 50 decibel, and for that part the signal to the bit rate, okay, the bit rate increases, it's linearly increases, okay, it's linearly increases through it and goes through to the limit out of that. So if the signal to noise ratio SNR is higher, you can get the better uh, bit rate. But why it is not necessary to written here the unattainable reason? That means it shouldn't be go through to like that. That's not the unattainable reason. So it should remain in that particular section. That means that's the maximum pathway. So it can't be there. So it's known as the unattainable reason. Okay. Let's go to the next section. Okay. Now that is the Shannon's limit, and the Shannon limit we can find out the Shannon limit from there. Okay, look over it. So that is the Shannon's capacity theorem. The W or B is similar as the bandwidth of the channel, the log to 1 plus SNR. So after that, if we find out this type of thing, just make the channel capacity or in the relationship with, we can say, with signal to noise ratio. How can you get that? If capacity is multiplied with the signal power, sorry, Yes, signal power. It is its signal power can be gettable by the signal bandwidth, or you can say signal bits with the capacity, and the W is the bandwidth. If you just accumulate the bandwidth through to the noise power, so you can get the noise power, total noise power out of it. So just replace the signal power and noise power to that, you can get this. So if the bandwidth is limitless, that means infinity or much more bigger, so the ratio will be tends to 0. So we get by calculating this minus 1.6 dB. That's the Shannon's limit. So okay, that's the unattainable region come forward. There exists a limiting value of EVN0. What is EVN0? EVN0 is the primary noise power and primary signal power. So that's the you can say that is you can say if SNR, signal to noise ratio, is formed as dB or decibel, so EVN0, that is the signal to noise power, that's the signal power, actual signal power and noise power are related to this. There can be no error free communication at any information rate. That means there are some errors. By increasing the bandwidth alone, the capacity cannot be increased to any desired value. So there are two particular points that we can find it out, that there is no channel or error free communication at any information rate, that can Shannon state, and there are increasing the bandwidth alone, the capacity cannot be increased to any desired value. There are other factors too. So these are some limits. So again we get the value here. So if we go through to this, that's the beats per second per hertz, you can say unattainable region are there. So why in which part is unattainable region? So after the calculation we find out the unattainable region, that is minus 1.6 decibel. And as you can see in the previous slide, that is the SNR decibel. Okay, now it has been converted to the EVN0 decibel. So you can find out the limit and the linear, what is the practical regions and what is the unattainable region, you can find it out. So there are a lot of things of Shannon's limit. So these are another factors, that there are another schemes right there. There is MPSK, that means phase shift keying. MQM, M means the number, okay, the number. If you raise the number of bits, at you can say a constellation diagram, if you would use 2 bits or 2 levels of communication, that's M is equal to 2. If you use 4, that's 4 FSK, 8 FSK, 16 FSK, 2 to the power n. The number of bits could represent the number of M. M is equal to 2 to the power n. That's the thing. So as you can see, the number of M roundabout gets higher, so the bandwidth is not limited, it is just go beyond, and we have a good type of communication right there. Just think about it. Okay, there's the MPSK and MFSK. The difference between MPSK and MFSK with respect to the KK factor is the main factor when we use the PSK and FSK scaling. That's the error probability plane. We will learn later on that. So that's the MRI signal. That's the part that we want to know, what is the MRI signals, the basic part. The MRI signal is a part of a signal that we know there are some modulation schemes there. There's PSK, FSK, and QPSK, QM, lot of things. There are a lot of things, but which bit, okay, which band efficiency it will work, that is dependent on the MRI signal. We will know in the another lessons. It will come along to the next lectures. Thank you very much for being with me.